Section 2.7, the precise definition of limits. So far in this chapter, we've been doing a lot of work with limits, and we've been basing some of the work we've done to evaluate limits on some theorems we were given. But the proofs of those theorems need a tight definition or a rigorous definition or a precise definition of limits in order for them to be really and truly proven. And so far what we've been working on is a loose definition, which is why we haven't looked at the proofs ourselves. So in this section, we're going to see what the precise definition of a limit is, get a feel for how it works, and do a couple easy proofs, but we'll leave all the messy proofs to the author of the book. All right, let's jump in and start exploring this topic. Recall, let f be defined around a, but not necessarily at a. Then the limit as x approaches a of f of x equals L means that f of x is arbitrarily close to L for all x that are sufficiently close to A. That was kind of our loose definition, or even looser, we said as x gets close to A, f gets close to L. But what we want to really make precise is, what do we mean by close? So let's move towards that precise definition. So we'll do a little scratch work and then we'll formalize it in the box below. So if f of x is close to L, then what we mean by that is the difference between f of x and L will be small. And that's still vague, so we're going to have to tighten that up in the box below. And since x is sufficiently close to x minus a, we'll want that to be small also. So how do we get to this idea of saying the distance between f of x and its limit is small and the distance between x and a is also small? So we do that by talking about the absolute value being less than some arbitrarily small number, and since it needs to be arbitrarily small, we'll use a variable. So we want the distance between x and a, which would be the absolute value of the difference of x and a. We want that to be arbitrarily small, so we're going to say we want that to be less than some value delta, which is just the Greek letter, so it's like we're using D here, but we're doing it in the Greek alphabet. And remember that we're supposed to be near a, but not at a, so we want the distance between x and a to be greater than 0, so we're not looking at what happens when x is equal to a. All right, so that's kind of how we're going to handle the idea that x is close to a. We're going to say the absolute value of x minus a, which is the distance between x and a, is less than delta, and we'll usually think of delta as some small number. And then we'll do the same thing for the distance between f of x and L. To keep that small, we're going to say the absolute value of the difference between those two is less than epsilon. So that's like the Greek letter E. I'm going to try and clean that up a little bit. I can't do a great epsilon, but it's like a little bit of a fancy E. I'm describing it to you, but there's one down here. So that's what it's supposed to look like. I did my best. All right, so let's take all that now and move it to a precise definition of a limit. Assume f of x exists for all x in some open interval containing a, not necessarily at a. So f of x doesn't have to be defined at a itself, or it could be. It's not important. And we say that the limit of f of x as x approaches a is L. Okay, so that's just all this, right? So if we want to look at the limit as x approaches a of f of x equals L, how do we do that precisely using those epsilons and deltas we talked about above? Well, what we would do is we'd say the limit as x approaches a of f of x equals L if, for any value of epsilon that's greater than 0, we can always find a delta that's greater than 0, such that as long as the difference between f of x and L is less than epsilon, such that f of x minus L will always be less than epsilon whenever 0 is less than x minus a is less than delta. The 0 part, again, is just making sure that we're looking at x's that are close to a and not at a. So really what we're saying here is we want it to be true that if we're given any epsilon greater than 0, we can always find a delta greater than 0, such that the difference between f of x and L in absolute value will be less than epsilon whenever the difference between x and a in absolute value is less than delta. All right, let's get a visual on that, and then we'll look at some examples because we need all that for this to really kind of sink in more. So we have this claim that as x approaches a, f of x is approaching L. So thinking of that visually. If we're moving along this line, getting our x values closer and closer to a, so here's our a, that as we move on the graph and get closer to that a, the height is going to move closer to this height, which is the L. So now the game we play in doing the proof is they give an epsilon greater than 0, and we need the distance between the function and the limit to be less than epsilon. So what that really means is they're kind of challenging us like, hey, you said that f of x is going to get close to L. Can you guarantee it'll be between these two red lines? Can you guarantee that it'll be in between the limit minus epsilon and the limit plus epsilon? And our goal is to figure out some way of saying, yeah, we can guarantee that'll happen. Just make sure that your x gets between these two lines, and if it does, the value of the function, we'll just keep grabbing colors here, the value of the function, which is in between those two lines, purple, will always end up staying between the two lines, red. So in this game, the epsilon's always given first, and they give us this horizontal strip and say, if the limit really exists, you should be able to guarantee that you can stay, that the function's height can stay in between these two horizontal lines. And if the limit really exists, we're going to be able to say, yes, we can guarantee that. Just make sure that the value of x stays between these purple vertical lines, and then that'll happen. All right, now expanding on that idea from the previous page, let's look at some visuals from another example. Let's look at the limit as x approaches 4 of the square root of x, which is equal to 2. And that should mean, according to this definition, that the absolute value of the difference between the function square root of x and its limit 2 will always be less than epsilon whenever the distance between x and 2, so the difference in absolute value, is less than some delta. And if you look at that in terms of the picture, suppose they gave us an epsilon like this, and we added and subtracted from the limit and said make sure you stay in between those two lines with your function. Someone else comes along and says, yeah, just make sure you stay within this distance of 4, and then the square root of 4 will stay within that horizontal distance of 2. If the limit really exists, they should be able to make how close they want the square root of x to get to 2 get smaller. And we should be like, that's fine. We just need to get closer with our x value to 4 to make that happen. And then we achieve that, and they're like, okay, but we want it to get even smaller still. Can you make that happen? And we say, yeah, just make sure that x gets closer to 4 than it was before, and then that'll happen. All right, that's all still very theoretical. Let's look at some specific examples to try and get a little bit of a better handle on what's going on here. And then we'll slowly move this to the point of the proof where we really try and do the arbitrary epsilon and arbitrary delta. One thing that can help it sink in a little bit and start to make some sense is to get away from the arbitrary epsilon and deltas and use some specific ones. Let's play the game a little bit where they give us an epsilon and we try and find a delta that does what it's supposed to. So let's look at an example with a graph and see what we can do. So assume the graph shown satisfies the limit as x approaches 4 of f of x equals 5. Determine the largest value of delta satisfying each of the statements below. So we want it to be true that if the distance between x and 4 is less than delta, then the distance between the function and 5 is less than 1. So this is our function right here. Let's get back to some normal colors. So here's our function. So what's this 5? Well, according to what we've been doing in the definition, that would be the L, and then this would be the epsilon. So if we wanted to do the picture stuff that we saw up above, then let's draw horizontal lines where we take that distance that they're challenging us to get our function within 1 unit of 5, and let's take the limit 5 and draw that, and then let's draw a line that's 1 unit above and 1 unit below. And we're being challenged, can you make sure that the height of the graph stays in between those two horizontal lines? And the idea should be, well, as long as we stayed between this point and this point on the graph, we're always staying between the red lines. So how far does that mean that we can move away from 4 and still have that happen? Well, we could move all the way over to here on the right, or all the way over to here on the left, and if we stayed in between these two green lines, then that guarantees all parts of the function are in between the red lines. So now the last part is, and this is the part they are challenging us to do, was to find delta. So, sorry, let me get to highlighting here. So they wanted us to find the largest value of delta that will make that work. Well, delta, right here, is the distance between the x value and 4. So the distance between x value and 4 on the right is this distance, and on the left, it's this distance. So in this case, both of those distances are 3. So it looks like the distance on the right is 3, and the distance on the left is 3. So we could end up saying, all right, as long as you make sure that x minus 4 in absolute value is less than 3, that will imply that f of x minus 5 is less than 1. So our delta is 3. So that's our answer. All right, let's try it again. And I think when we try it again, it would be nice to try it again with a clean graph. So let me go ahead and get rid of all this stuff, and we'll do it again. So coming down to the second example, they want us to play the same sort of game, but this time they want the difference or distance between the height of our function and the limit of 5 to be half a unit. So here's our limit 5, and they're saying we want to make sure you stay within half a unit of that. It could be half a unit above, or it could be half a unit below, but make sure you stay in between those two. And then we come along and start inspecting and say, well, don't go further out than this or this. And then we try and measure how far away is that. So let's draw in the vertical lines that go with that. Kind of missed that. Let me draw that a little better. Okay, so there's our vertical lines on the left and the right. Here's 4. How far away does it look like you could get to the right-hand side and stay within the horizontal bounds? It looks like probably 2. If the symmetry is right, it would be 2 on the other side, but it actually looks a little bit bigger here. So let's say this was 2.2. Well, what should we choose for our delta if you could go as far as 2 units to the right to achieve the goal, or as far as 2 units to the left? Well, if you want to play it safe and you want to make sure that whenever x minus 4 is less than delta, that you know that f of x minus 5 will be less than 1/2, then you better make the delta the smaller of the two numbers, so I would go with that one. And I would say let's choose delta equal to 2 this time. And then if we do that, it should be the case that whenever x minus 4 is less than 2, it will be the case that the absolute value of f of x minus 5 is less than 1/2. So there's some specific work with epsilons being given and us choosing the delta. Notice it's always the epsilon first, and then we choose a delta that'll satisfy what they wanted to happen. All right, let's go ahead and move on to an example now where we actually know the value of the function. So the last one, they just had this generic f of x. This time we're going to look at one where we know that f of x equals x cubed. And the thing that's going to be different this time is they're not going to give us the graph, but we'll use the graphing calculator to explore the same sort of things we did on the one above. So let's jump in. Suppose f of x equals x cubed, and note that the limit as x approaches 2 of f of x equals 8. Well, we can see that very easily. This is a polynomial, so if you plug 2 in for x cubed, you get an 8. So we can kind of check that that is indeed the limit by direct substitution. And then for each given value of epsilon, use a graphing calculator to find a value of delta such that f of x minus 8 in absolute value is always less than epsilon whenever 0 is less than absolute value of x minus 2 is less than delta. And they give us an epsilon equal to 2. All right, so we want to recreate the graph that we just saw above and then go through the same sort of path to figure out what delta will work for us. So to recreate the graph, the first thing you want to do is just graph the function. So let's switch over to the graphing calculator and enter that in. So our f of x here is y equals x cubed. So we'll go ahead and enter that. And let's just jump in and look at the graph real quick. So there's our kind of standard x cubed function. We're looking at the limit as x approaches 2, so that should be that 8 value right there. So we can see that visually, but we want to explore the epsilon delta proof idea on this picture. So to do that, we need to draw the horizontal lines that relate to the epsilon. So let's go back into the graphing calculator and think about what horizontal lines would we draw. The epsilon they gave us is 2. So they want us to stay within 2 units of the limit, which was 8. So 2 below the limit of 8 would be a 6. And then 2 above the limit of 8 would be a 10. So I'm going to draw a horizontal line, y equals 6 and y equals 10. And I'm going to go ahead and do some adjustment on the scale here so we can see this a little bit better. But our limit was 8, and I've drawn horizontal lines 2 units above that and 2 units below that. And according to this kind of game we're playing, they've just said, all right, we challenge you if the limit as x approaches 2 really is y equals 8, then you should be able to get close enough to 2 that you can guarantee that you'll stay in between these horizontal boundaries that are 2 units above and below the limit of 8. So how do we do that? Well, we look at the 2 intersections between our graph and those lines, and where do they occur? On the right, it looks like it's 2.1544, and on the left, it looks like it's 1.8171. So if we stay in between those 2 points of intersection, 1.871 and 2.1544, then we're always going to stay in between the 2 red lines. So let's switch back to the notes and see what does that mean for us. So we found 2 boundaries there, so I'm going to go ahead and write those down. The boundary we found on the left was approximately 1.8171, and the boundary we found on the right was approximately 2.1544. And we could see graphically that as long as we stayed between those 2 x values, we were going to be in between the 2 red lines. So what does that look like graphically for us here? Suppose we imagine a number line with 2, and we're saying we need to stay in between 2.1544 and 1.8171. Well, the way the game's played, we don't list a left boundary and a right boundary. What we're supposed to pick is a value of delta that as long as you stay within that distance of 2, you'll be okay. So I'm going to argue that we have 2 potential distances here. We have this distance from 2 to the right boundary, and then we have this distance over here from 2 to the left boundary. So what we want to do is figure out what are those 2 differences, and we can just do that as a subtraction on the calculator. So let's head back over to the calculator and do the subtraction. So take the right-hand boundary, 2.1544, subtract 2, and we can see the distance from 2 to the right side is 0.1544. And then take 2 and subtract the left boundary, which was 1.8171, and we can see the distance from 2 to the left boundary is 0.1829. And we saw in the previous example that when you're given these 2 potential different sized values for delta, that what you need to do to make sure you stay in between the red lines is make sure you stay within the smaller distance of the number 2 in this case. So given these 2 choices for delta, we'll go with the smaller one, 0.1544. So let's go back and write that down. So we're going to go with delta equals 0.1544. And that's going to be our answer for this question. So we're claiming as long as you make sure that x minus 2, that you make sure that the distance between x and 2 is less than 0.1544, then you will always be making sure that the difference between your function and the height 8, or the limit of the function at 2, is less than epsilon. All right, let's play the game again with a different epsilon. So this time they want us to change the epsilon to 0.5. So what does that mean in terms of our picture right here? Well, instead of being able to go from 8 up 2 and down 2, which is where we got the 6 and the 10, now we're just going to go from 8 up a half and down a half. So going back into here, if we went down a half instead of 6, that would be 7.5. And if from 8 we went up a half instead of 10, that would be 8.5. If we go back to the graph, we're seeing that what we're saying is, all right, we've got some narrower lines that we want you to stay in between now. And they're challenging us, can you find a distance that as long as you stay that close to the number 2, you'll always be in between the red lines? Well, we know we'll be in between the red lines if we stay in between the intersection on the right, which through trace I can see is 2.0408, and on the left, 1.9574. If we stay in between those, we know we'll stay in between the two red lines. So we're going to write those down and then try and convert that to a distance. So back to the notes. Looks like the x on the left that we'd want to use is approximately 1.9574. And the x on the right that we would want to use is 2.0408. Then we have that same idea of, well, which one of those creates the smaller distances. So we go to the calculator and we do the subtraction, and whichever one is smaller, that's what we're going to pick for our delta. So let's go see what that would be. So back to the calculator, exit from the graph, go and do some subtractions just like we did up there, but this time our right boundary is 2.0408 minus 2, and our left boundary, so we'll do 2 minus our left boundary, so 2 minus 1.9574, and we get 0.0426. A quick comment on like, why do I subtract in a different order? Why isn't 2 always first or always second? We're talking about delta as a positive number, so I'm just always making sure I subtract the bigger one minus the smaller, so I get the distance as a positive. And then, like we said on the last one, to make sure that you stay in between the two red lines, you have to go with the smaller of these two choices of delta. So in this case, it would be the 0.0408. So we'll go back and write that down. 0.0408 would be my choice for delta. All right, so just wrapping this up with a note here. For the limit as x approaches a of f of x equals L, when you find the two x values that will potentially be used to find the value of delta, you always want to use the x value that is closer to the value of a, which on the example we just did was the number 2. So you look at how far each one of them from that a, or in the case above the 2, and whichever is the smaller distance, that's the one you go with. So I was able to do those intersections really easily on the app that I use, Graph and Calc 83. But what if you're using a standard TI-84? Let me go ahead and write down what the steps are. The first thing is do the graphs. That's similar to what you saw me do on my calculator. So you do that first. And then after you do that, the next step is to hit the second button and then look for the key that says Calc. That's above intersect. And then after you do calc, you'll choose intersect. Sorry, I think I said calc is above intersect. Calc is above trace. So you're going to draw the graph with the horizontal lines on there. You're going to hit second, calc, and intersect. And then it's going to make you do some choices. So it wants you to choose your graphs. And then choose a guess. And then finish. So those are the steps, but I'm going to describe what they look like to you as well. So when I say to choose the graphs, right after you do second calc and intersect, it's going to be showing you a blinking light on one of the graphs, and it's usually on y1, which would be the x cubed function for what we just did. And they're asking you, is this one of your graphs? And you just press enter to choose that graph. And then it'll be either on the y2 or y3, which is one of your horizontal lines, and you press enter to choose that graph. And then it'll say, how about this for a guess at your point of intersection? It'll have a blinking point. What I would suggest is you move it with the arrow keys close to the point of intersection, and it'll show you x and y's, but those are still a guess. So just press enter one more time, and that's how you finish. But you have to do it twice. So when you go back through the second time and you're looking at the graph and you hit second and calc and intersect, for the first graph, still choose y equals x cubed, but if you chose, like for the horizontal one, y equals 6 the first time, now choose y equals 10 the second time, so you can find the point of intersection with the other horizontal line, move your guess over close to where it looks like the intersection is, press enter to finish. Make sure that it says intersection when you write down the x value. If it still says guess, that's just an approximation, and that's not good enough. All right, so far we've seen the precise definition of limit, and then we've looked at some visual examples of what that meant. We've played around with the idea of if they gave us an epsilon, could we find a delta that works? But we haven't actually seen what it all looks like when you put it together for a proof. So I'm going to show you two examples, one kind of saying what the process is, and then another one just to kind of see it a second time. So let's look at the process of constructing the limit proof using that precise definition. So our first example, use the precise definition to prove that the limit as x approaches 5 of 2x minus 3 equals 7. Now through direct substitution, we see if we plug in 5, we get 2 times 5 is 10, minus 3 is 7. So we know from previous things that really is the answer. But what if we were asked to prove it using the definition? What would that process look like? So what you always want to do is kind of have a scratch work step and then a write the proof step. So this step 1 is our scratch work step. So what you're going to do is start with f of x minus L, and you're going to manipulate that using algebra to try and rewrite it in a form that includes x minus a in absolute value. And once you do that, it should allow you to see, so you're going to solve for that x minus a once you get it included, and then that should help you see what a good choice for delta would be. So that's a little messy still. Let me show you specifically what that looks like for this problem. So start off with the absolute value of f of x minus L in absolute value, and we're going to say that's less than epsilon. Now we're going to start plugging things in from our function. So what is f of x in this one? It's whatever was inside the limit, so 2x minus 3. And then subtract L, which would be the other side, and set that to be less than epsilon. And now just start simplifying a little bit. So in the absolute value there, you could combine these two like terms. So that would be absolute value of 2x minus 10 is less than epsilon. And now go look at what your x minus a piece would be. So in this problem, that would be the absolute value of x minus whatever x was approaching, which in this case is 5. That's the part you want to get to show up. And I can kind of see where that would come from. If you took what was inside there and you factored out an absolute value of 2, then what would be left inside would be the absolute value of x minus 5, which is less than epsilon. And that right there matches that piece. So that's kind of what our goal was. So then next, solve that so that the x minus 5 is by itself in absolute value. So we're going to include that part in what we get by itself. And then you'll be able to make your choice of delta. So to get that absolute value by itself, I would divide both sides by the absolute value of 2, which is just 2. And then what does that give me? On the left, these 2's will have canceled. I'll have the absolute value of x minus 5 is less than epsilon over 2. And once you do that, where you get the absolute value of x minus a by itself, whatever it is you see on the other side, that's what you're going to choose to be your delta. So we're going to choose delta to be equal to epsilon over 2. Remember in the game we play, they chose epsilon before we chose delta. So basically in this case, we're saying whatever epsilon they choose, we would choose exactly half of that. So now let's see what the proof looks like. Let's suppose that the enemy, if you will, gave us an epsilon that was greater than 0. And then we're going to assume that the absolute value of x minus a is less than delta, where delta equals epsilon over 2. And that should get the job done. All right, so here comes the formal proof now. Suppose that x minus a is less than delta. What does that mean? That means that x minus 5 is less than epsilon over 2. And now what we're going to try and do is kind of work backwards from the scratch work we did up here and end up at the f of x minus L. So we want to start trying to make this look like f of x minus L. So the first step in that would be to multiply both sides by 2 to get the epsilon by itself. So we'll do that on both sides. Get a cancellation here. So now we have 2 times the absolute value of x minus 5 is less than epsilon. Multiply that 2 into the absolute value, which you can do as long as it's positive. And we get this. And now we want to make this piece right here start to look like f of x minus L. So what does f of x look like? F of x was 2x minus 3. So we want to have that 2x minus 3 show up there. So let me just write 2x minus 3. What would I also have to put in the absolute value so it was still equal to that minus 10? That would have to be a minus 7, because minus 3 and minus 7 would be the 10. And that would be less than epsilon. So now what's good about what I've done is this is f of x, and that's L. So that means at this point I have that f of x minus L is less than epsilon. And it takes a while for this to really sink in and feel good, but we just proved what we were supposed to. They gave us an epsilon greater than 0. So that was right here. They gave us an epsilon greater than 0. We picked our delta to be epsilon over 2. And then we showed that as long as x minus a was less than delta, that ended up showing that f of x minus L was less than their epsilon. And that's what you need to have happen for the proof to be solid or really done. So there's your first look at a proof. A little bit rough because we were kind of doing the scratch work and all that, and it's also very theoretical, so it's hard to digest, and just once probably isn't enough. So we're going to look at one more, and hopefully that'll help it click a little. But then after that, you'll play around with it in homework, and that'll help some too. All right, so here we go with one final example. Use the precise definition to prove that the limit as x approaches negative 2 of 1/2 x plus 3 is equal to 2. So we're going to start off with some scratch work. And that scratch work always starts off by playing around with f of x minus L being less than epsilon and starting to plug in and see what that looks like. So our f of x is always what's inside, and our L is always what's outside. So for f of x, we're going to have 1/2 x plus 3, and then for L, we're going to have the 2. And that's supposed to be less than epsilon. And then we're going to try and manipulate that so we can see the absolute value of x minus a inside of this absolute value expression right there. We want to make x minus a show up. So what is A? A is that negative 2. So what does x minus A look like? It would be x minus a minus 2. So that's what we're trying to get to show up somewhere inside of that absolute value. So going back to our scratch work, let's just simplify what's inside it first. We have 1/2 x plus 3 minus 2, so that's plus 1, and is less than epsilon. And then how about that half? Well, we don't really want the half there. We just want, if we look at our goal is up here. We just want the absolute value of x minus a minus 2. So we just want an x, not a 1/2 x. So one thing we could do to make that happen is multiply by 2 on both sides. And if we do that, these 2's are going to cancel. And we're going to end up with the absolute value of x plus 2, using the distributive property there, is less than 2 epsilon. And now we don't want x plus 2, we want x minus a minus 2, so we'll just change that plus to a double negative. So the absolute value of x minus a minus 2, and now we've got that x minus a look, and it needs to be less than 2 epsilon. And since we want x minus a to be less than delta, this tells us what our choice for delta should be. It should be this 2 epsilon. So now let's get to work on the actual proof. So scratch work to help us pick our delta. Now let's see what the proof itself looks like. So let epsilon greater than 0 be given by the enemy. We now know what a good pick is. We're going to pick delta equal to 2 times epsilon. So whatever epsilon they gave, we can go twice as big. And we want to show that does the job. So suppose that x minus minus 2 is less than delta. So that's x minus a is less than delta. What does that imply for us? It implies that x plus 2, simplifying the double negative, is less than 2 epsilon, plugging in our value of delta, which was 2 epsilon. And then we're trying to get to f of x minus l, and f of x minus l has that 1/2 in the inside. So we're trying to work backwards here. So that step where we multiplied by 2, we're now going to multiply by 1/2 on each side and do the opposite. So what are 2 good things that happen when we multiply by that 1/2? Well, we get just epsilon on the right. That's going to be good. And we get a 1/2 inside of our absolute value, which is also going to be good. So distributing in that 1/2, we get 1/2 x. And then 1/2 of 2 would be plus 1 is less than epsilon. So this is great if 1/2 x plus 1 is equal to f of x minus l. Let's go back up and look at what f of x is. F of x is this piece, l is that piece, so we probably want to split that 1 up into the 3 minus 2. So we're going to come down here, we're going to change this to 1/2 x plus 3 minus 2 is less than epsilon. This piece is f of x, that piece is L. So now we can say that that implies f of x minus L is less than epsilon. And we've won the game, so the proof is done. So how did we win the game? They picked an epsilon greater than 0. We picked our delta to be 2 times epsilon. And then we showed that having x minus a less than that delta implied that f of x minus L is less than epsilon, which is what the precise definition of limit guarantees. Just a quick word of caution. It took me a long time as a graduate math student to really deeply understand this process. So, You don't have to become an expert at these epsilon delta proofs. These are only the simplest type that I'm showing you, so we're going to play around with these a little bit so we get a feel for it. I just want you guys to know as we move forward that all of our limit theorems are based on a solid definition and proven with that solid definition. So we're playing around to get familiar with the definition. Don't freak out if you have some uneasiness about it. Just do the best you can to get through those homework problems and know that we are built on top of a solid foundation. All right, that wraps up 2.7 and therefore chapter 2.